Okay, so for preliminaries, we're going to talk about sets and set notation. It's just we use this knowledge and this notation a lot in linear algebra. So we're just gonna, you may be familiar with some of it and not with some other stuff, but we're just gonna go over it all. All right, so a set is a well-defined collection of things, elements or numbers. So well-defined means that there's no ambiguity as to whether or not an object belongs in the set. Okay, so you can always tell, if I hold something up and I say, is this in the set? You can very easily say yes or no. There's no like, ooh, I'm not sure. You know. So for example, here's a not a well-defined set. In a certain town, there's a barber who shaves those and only those people who do not shave themselves. Consider the set of people in the town who do not shave themselves. Is the barber in this set? Right. So if he does not shave himself, then the barber is supposed to shave him, so he would shave himself. Right? It's kind of circular. So it's not a well-defined set. You can't, there's some ambiguity about whether or not the barber is in this set of people who do not shave themselves. Good point. Thank you. Okay, a set can be finite or infinite. You can have a finite number of elements or an infinite number of elements. Some common sets of numbers are the integers, the rational numbers, the real numbers, the complex numbers. Those fancy letters are just shorthand, Z with an extra line. That's a typo. It should just be a plain old R right there. Z with the extra line or a bold Z sometimes represents the set of all integers. And Q with the extra lines represents all rationals. That is fancy R, all real numbers. And fancy C, complex numbers. Those would be numbers that have like I in them. So there's several ways to describe the elements of a set. 3 common ways. You could just describe it in words. You could use the roster method where you just list every element in the set inside some curly brackets. Order that you list things in a set doesn't matter. Or you can use set builder notation, which generally looks like this. You have a curly bracket X, vertical line, which means such that. So all the X's such that X fulfills some condition. So this symbol that looks like a weird looking E means is an element of. So for example, I could say 8 is an element of Z. 8 is an element of the integers. All right, so let's talk about the rational numbers. We want to describe them using all 3 methods. Even though we can abbreviate it as Q, let's just remind ourselves what they are. In words, what are rational numbers? Fractions, yeah, where the top and the bottom are integers. Yeah, because this one got me once. That's a fraction, but it's not rational, right? Yeah. So the top and bottom, any number that can be written as a fraction where the top and the bottom are integers. Okay, so the roster method, I want to list every possible rational number. This one's tough because they're infinite, right? And it's just not as straightforward as listing the whole numbers, like 1, 2, 3, dot, 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 right? So here's how most people do this. It's not perfect because there's some repetition, but that's okay. As long as we get everything in there, it'll be all right. So first I'm going to start listing all the rational numbers that have 1 as a numerator. So I could have 1 over 1, I could have 1 over 2, 1 over 3, etc., right? All the fractions that have 1 on top. And then I move to all the fractions that have 2 on top. 2 over 1, 2 over 2, 2 over 3, etc. 3 over 1, 3 over 2, 3 over 3, etc. Right? And then you just keep doing that. That's how I write out my infinite list. So that you can see there's some repetition, like 1 over 1 and 2 over 2 and 3 over 3 all represent 1. But I think I'm going to hit every single rational number by writing it out this way. And then set builder, I would say this is the set of all numbers that look like fractions, right? Set of all fractions. So I'm going to put P over Q such that what has to be true of P and Q? Must both be integers. So I put such that P, comma Q are elements of Z. Definitely the most compact, succinct way of writing it is the set builder. That's typically true of infinite sets. A set with nothing in it is called the empty set or the null set, and you can put 2 curly brackets with just nothing in it, or you can put a circle with a line through it, but you can't put the circle with the line through it inside the curly brackets. It just doesn't make any sense. All right, so one way to look at, one way to describe two-dimensional space is the coordinate plane, right? The x, y axes. And we often call that R2 because it's got made up of 2 real lines, the x and the y, are both real number lines. So call it R2. Every point is given a set of coordinates, x comma y. But in this course, we're often going to use a vector to express the coordinates. So you put x, y in a vertical form rather than x, y across. They mean the same thing. And your book typically in the text will use the vertical x, y, but often in the solutions, they'll write horizontally to save space. So you just be able to sort of translate between the two. So if I want to describe R2 using set builder notation, I'm going to use the XY coordinates and vertical vector notation. So set builder always starts with curly bracket, and it looks like vectors XY, the set of all vectors XY, such that where do X and Y have to live in the reals, such that X and Y are elements of R. So this is R2. That's how we would describe the coordinate plane, two-dimensional space, using set builder notation. Okay, turning to page 4. So most of this handout is for homework, but I want to go through a little bit of it together. So a proof is just an argument. It's an argument designed to convince someone that a statement is true. It's akin to writing a piece of music. The process is both creative and logical. There are a number of rules and customs that we follow, but there's no routine or procedure that you can just do every time to write a proof, right? There's no routine or procedure that you can do every time to write a song. It's a skill and a knack you'll develop over time. You'll get the hang of it, patience and practice. There are lots of different types of proofs, lots of different ways you can argue. Direct proof, proof by contradiction, and proof by induction are the 3 most common. But we're just going to start with direct proofs. Most theorems can be written in the form if something, then something else, right? So if triangle, then square. Here, triangle and square are themselves statements, things which are either true or false. And the statement triangle is called the hypothesis, and the statement square is called the conclusion of the theorem. So the if part is the hypothesis, the then part is the conclusion. In a direct proof, you assume that triangle is true. You assume the hypothesis is true. And then you argue, 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 and then you conclude that the conclusion must also be true. So the proof will sound something like, we assume triangle is true, therefore such and such is true, which means that blank is true, so square must be true and the proof is complete. So the first step typically is to take your theorem and write it in if-then form, right? So we're going to prove that the sum of two even integers is even. Let's just like convince ourselves really fast. Like 2 plus 6, 8. Yeah, that's even. 4 plus 10, 14. Yeah, that's even. So you might do like 3 or 4 little checks, make sure that you're not wasting your time trying to prove it. And then you'll be like, okay, I'm pretty convinced I'm going to try to prove that it's true for every single even number, right? You can't test every single even sum of two even numbers because there's too many. So we have to prove that it's true all the time using a proof. All right, I'm going to skip over this part and we're going to write it out together. Theorem 1, we're going to take without proof. We're going to assume that when you add two integers, you get an integer. And when you multiply two integers, you get an integer. So we're going to use this definition, this Theorem 1 and definition 1. We're going to use those to prove Theorem 2. So our definition of an even integer is that an integer n is even if it can be written as 2 times something. So typically when you learn about evenness, you think it's a divisible by 2, right? 2 goes in an even number of times. So this is just an alternative way of saying that. So pick any even number. Let's pick 20. It can be written as 2 times 10, right? Any other even number, 34, it can be written as 2 times 17. So any even number can be written as 2 times an integer. So that's what we're going to use as our definition of even. All right, so if I want to prove the sum of two even integers is even, first I'm going to change it to an if-then statement. So if n and m, those will be our two even integers, are both even, then what can I conclude based on this theorem? The sum of them is even. Then n plus m is even. Okay, so I've written it in if-then form. If I have two even numbers, I can add them together, and I'll also get an even number. So my proof. In a direct proof, you assume the hypothesis of the theorem is true. So I'm assuming I have two even integers, n and m. Assume n and m are both even. That's typically your first step of a direct proof. Assume the hypothesis. Then we draw some conclusions from that assumption, right? So if n and m are both even, that means that I can apply this definition to both of them. I can write n as 2 times an integer, and I can write m as 2 times an integer. Okay, so I'm going to say, by definition, n equals 2k, and m equals 2j for some k and j in the integers. I have to use two different letters, k and j, because n and m aren't necessarily the same even number, right? So n is 2 times something, m could be 2 times something else, right? So I use k and j. All right. Thus, let's see what happens when I add n and m together. N plus m, I just do a quick substitution here, is actually 2k plus 2j. Factor out a 2, right? And so this is k plus j. But what's an integer plus an integer? Another integer, right? So, right? So n plus m now satisfies the definition of even. It's 2 times an integer. Okay. By definition, I should probably define L. I'm actually going to be a little informal here. I'm going to write 2 times an integer. So n plus m is even by definition. So when you first start learning how to write proofs, it feels stupid. Like I know that an even plus an even is an even. Why do I have to write out a formal proof for it? It's just for practice, right? You practice with things that you know and feel comfortable with, and then you work your way up to proving things that don't feel intuitive and actually need proof. All right, so I'm going to pause here and have you turn back to page 2 and work on your group activities for a little bit. Then we'll come back together and do another lesson.